actually going to show you a different criterion first, which is on the T, and then I'll show you the Poincare Bendixon criterion. So again, this is a little bit of like starting with the history of I didn't have a computer, I don't have Mathematica, I have nothing at my disposal except punch cards. So let me figure out what's going on first before I send this punch card off. So there's some of that. Then as we gravitate towards the 1980s or so, the computers start being more prevalent. I couldn't get the thing off my wall with the Edward Lorenz thing. I made that on one of the first iterations of Mathematica in 1990. So that's where you start to see, like at my desktop, I can actually run something before I even start doing analytics. But one of the things people wanted to know is, do I have some crappy behavior before I start putting in punch cards? Can I get to where you were on that computer before I throw in the punch cards, because it takes forever to do? And so there was these criterion that were made. I think I will start with Poincare Bendixon. These are amazing theorems. Poincare is a very cool name. And I wrote it as a checkability theorem, but it's really hard to use. And your book is pretty interesting. They give you the theorem, the criterion, and then they ask you to, they have a whole bunch of homework problems using something called the Dulac criterion, which is a corollary of this, but they never gave it in the book. So I looked at these homework problems and went, well, this is actually an important homework problem, but where in the book do they explain how to do this problem? Nowhere in the book do they explain how to do it, but it is important. Let's suppose I have just a two-dimensional system like this. Now I'm going to write it like this. Check the following are satisfied. E, have continuous partial derivatives. On a region D. In the previous example, you can think of the region D as being like inside the unit circle. Like you don't know the picture. So pretend you don't know the picture. So if you don't know the picture, you say, well, I think something might be happening with the unit circle. So let's make my region D the unit circle. And let's suppose that I have another region, D1 bounded, side D. And then R is the region. The boundary of D1. You can think of it as like D1 to be your unit circle if you want to. So the unit circle in that previous example, I include the boundary of the unit circle. And you know that, let's suppose you did all that math and you figured out that R equals 1 is an equilibrium solution. So what does that tell you? That means that inside that circle, it can't cross the circle. It has to stay inside there because you have uniqueness of solutions. So let's suppose that there exists solution x of t, y of t that stays inside that region. So again, the unit circle, I know that all my solutions have to stay inside there because the unit circle is a solution, and the only other solution is going to be the equilibrium point, 0, 0. So everything else has to stay inside there. It can't cross another solution because then you'll lose existence of uniqueness of solutions. And so I have all those criteria. can't imagine what it's like to not have a computer. Like, some people that were in my cohorts, like when we were graduating, they embraced the computer. I was one of the first graduate students at Georgia Tech to use computing in my work. Again, I told you, like, when Wolfram Mathematica came out, like, I can actually go get my PhD now because minus signs don't matter. I'll plug everything into Mathematica, tell it to simplify, and I'm done. But that was not embraced by everybody. And so at that point, like, we're still teaching these things. It's in your book. But if you don't have a computer, how are you going to know what the solution looks like? You don't know anything when you're given an equation. And maybe it's a really important set of equations. Maybe it's the equations that govern how the air flows against a wing. It's an important set of equations. You can't mess those up because you're building an airplane, so you can't do that. You might have wind shear. You might have problems. So if you want to be right, you want to do all this first before you send your punch cards over, because there could be a mistake in your code. Now you can just throw it into ChatGPT. Like, I don't know how to tell you how I embrace that as well. Like, my coding just heightened up because I can throw things into ChatGPT and ask it to fix it. So you have to know something about your differential equation. So let's suppose I did this polar coordinate transformation of those initial problems, and I see, oh, look, r equals 1 is the solution. Pretend I didn't get to see the solution first. Now it's the first hint I have. A solution is a circle. That's a solution. The entire unit circle is a equilibrium value for the polar coordinate thing. So I know that I can say, okay, because I know that, I can make my region to be this. Inside the unit circle.
Just anywhere inside the unit circle?
Yes, because I know this is a solution. I know there's a solution here, down at the bottom. But there's no other solutions that I can make a guess. There's no other solutions inside there. I can apply this theorem now to say I know what happens. What's going to happen is either it's going to be a periodic solution inside R, but I know already R equals 1 is probably the only one out there, or it's going to spiral to 1. So it's going to tell me what that thing looks like without a computer. So they show this to you in the book, and then they say, by the way, it's really, really hard to check this. So if I gave you a problem and said, apply this, I won't do that. That's unless you really cross me. Somebody really crosses me before the semester's out, and I get that mad, which I hardly ever get that mad. Even my kids don't make me that mad. And one of them crashed the truck and totaled it last week, and I still am not that mad. So, huh?
I'm sorry to hear that.
Raising kids is tough. But my point here is that this is used in the pre-era of computers, and people worked really hard to put, like, the Van der Pol equation, the way they knew the solution looked the way it did, is because they applied this kind of theorem. And they talk about that in your book. But you can't use that. Like, this is too hard. And you definitely can't use it on a T. So if I ask a question like that, it's to set you up to fail. At least this question. And I won't do it. So, but you need to know this existed. You need to know this exists. That's how people did things. The one I can show you, which is not in your book, but they have a whole bunch of homework problems, is something called the Dulac criterion. Which I'll show you that on Friday, how to use it. There's one question, there's a whole bunch of homework problems, how to use it, but it's the non-existence of when can I look at something and say, I don't have this weird kind of behavior, I don't have to transform it in polar coordinates. I know that it's gonna not only converge to an equilibrium. That's a Dulac criterion. That one's important. That's a quick check, easy, and you apply it. So I'm gonna show you how to do that Friday. There's a T problem on it. I think it's one of the more easier ones to do, because you just check through the theorem. Sound good?